Hi students, this is lecture 3. It's about development of systems simulation. We will discuss some important terms to build a successful simulator. Okay, development of a system simulation has many parameters or many understandable things like input, output, and configuration of the system. This system block diagram explains some basic idea of a simple simulator. We have controllable inputs, we have uncontrollable outputs to the system, we have to get some output. Okay. The development process of a system simulation involves some or all of these following stages. Problem formulation. We have to understand the problem before we proceed in the simulation. This involves identifying the controllable and uncontrollable inputs. Some controllable inputs, we can define it as random variables in the simulation. Some uncontrollable variables, we can get it from recordings, from long sheets of actual real data and put it in the system. Or generate some random equations to do this, to do these inputs. Identifying constraints on the decision variables, defining a measure of performance, i.e. an objective function, and developing a preliminary model structure to interrelate the system inputs to the values of the performance measure. This is all about problem formulation. There's no such deep explanation we have to do with it. Just you have to understand that any simulation system has its input. Some of the inputs are controllable, some of the inputs are not controllable. That's it. Okay, the second term is data collection and analysis. Okay, how to collect data? You have collected many data in your studying in your degree, since from your first stage to the second stage, third stage. You have learned some basics in the laboratories to how to collect data for different types of inputs. Decide what data to collect about the real system. For example, if it's a electrical system, you can collect data by measuring voltages of nodes or etc. If it's another system, you have to know what is the inputs of what is the needed data for that system. How much to collect? Sometimes you need to collect too much information to make the simulator works better, or you can suffice, or you can collect a small number of data, and you can use some software to make these data more applicable. This decision is a trade-off between cost and accuracy. We all know that if you spend too much time and cost on collecting data, you will have better accuracy. But if accuracy is not that important, you don't need to make a big deal about collecting too much data of the system. This is all about data collection and analysis. Okay, the third development system simulation term is simulation model development. This acquires sufficient understanding of the system to develop an appropriate conceptual logical model of the entities and their states, as well as the events codifying the interaction between entities. This is the heart of the simulation design. For example, in terms of networks engineering, you have to understand what is routers, switches, and some nodes of your network or internet. For example, internet routing technologies, etc. This information will help you identify the logical model of the entities. Each entity, such as a computer, a router, a switch, or etc. You know what they are actually, how they work, how they collect data. In terms of networking, the data usually we consider in terms of packets, for example, and how they are states, if they are turned off or on or online or sleep states, etc., as well as events codifying the interaction, when it should start, when it should be shut down, and what time is important to check these devices or entities, and so on. This is the heart of the simulation design. Okay, no need for more explanation for this term. I think you will get a grasp of these terms automatically when you deal in an example. Okay, we have three very important terms that we will use in engineering in all aspects, not just in network simulation. We have a term called validation, we have another term called verification, and a term called calibration. We will visit each of these separately, but put in your mind, do not confuse with verification and validation. They are not the same. How? Let's read about them. In general, verification, the second one, verification focuses on the internal consistency of the model, while validation is concerned with the correspondence between the model and the reality. Okay, we said that simulation is representing a real thing in computer system, encoding or mimicking it, or making a clone of it. So validation means that how your system is similar to the real model or real entity. You are making a model and you are checking if it is real, if it's valid to the real to reality. While verification is different. The term validation is applied to those processes that seek to determine whether or not a simulation is correct with respect to the real system. More precisely, validation is concerned with the question. Okay, the question is very important because it gives you the big idea of what is validation. Are we building the right system? The answer is validation. Okay. While verification is, on the other hand, seeks to answer the question, are we building the system right? Okay. If you have the real system, if you choose to build the right system, then you have to do it accurately. If you do it arrogantly, it means that you've verified it. So verification comes after validation. Okay, on that, verification checks that the implementation of the simulation model program corresponds to the model. Validation checks the model corresponds to reality. I think it's clear enough. Like, first step is validation. You have to choose the right system to imitate the real system. The second thing is verification, which means that you build the system right, the model right. Okay, let's jump to the third term, which is calibration. You used this term before in laboratory, in electric circuit, I think. Calibration means, especially in oscilloscopes and other devices, we use calibration to make system works properly. Okay, checks the data generated by the simulation match the real observed data. Sometimes based on many noises or different temperature types, you need to calibrate your data generation such that it will be the same as the real observed data. Okay. The fourth type term to the development of a simulation system is input and output analysis. Discrete event simulation models typically have stochastic components. It means that the inputs we generate it on basis of stochastic components. You will say, what is stochastics? If you study it then you will know what is stochastic. If you don't study it, then just put in your mind stochastic means random. It's different than random, but since you have this is like a advanced course of you may not understand what stochastic means exactly, but I think you have studied in the probability and statistics. Just put in your mind stochastics means random components that mimic the probabilistic nature of the system under consideration. Successful input modeling requires a close match between the input model and the true underlying probabilistic mechanism associated with the system. Okay, it means that you have to address that input types. If you use input types, like what type of random variables you are going to use. Like Gaussian distributions is one of the stochastic components. What type of input you are going to use? Uniform, Gaussian, some other terms. We discussed it in the previous lecture. Okay. I'm going to give you a special tutorial for this type of terms to understand it very well. Okay, let's focus on the lecture right now. The fifth term is performance evaluation and what-if analysis. Okay, the what-if analysis involves trying to run the simulation with different input parameters under different scenarios to make the system, the model, perform in many conditions or under different scenarios. You have to make sure that different input parameters should be tested and see how the performance measures are affected. This is very important because in real system we can't use different input types all the time because we may not have it, or it is very difficult to have it. In simulation, you can use any input type to test your system performance. Okay, the sixth term is sensitivity estimation. Users must be provided with affordable techniques for sensitivity analysis. If they are to understand the relationships and trade-offs between system parameters and performance measures in a meaningful way that allows them to make sure system design decisions. To make sure the system design decisions. It means that some inputs or outputs are very sensitive to the inputs. So one test you have to do in your simulation is a sensitivity analysis. Okay, based on your understanding of the relationships or trade-offs between the system parameters and performance measures. It's self-defining actually. Some systems are very sensitive, some systems are not. So for system they are sensitive, you have to have a special sensitivity analysis before you undergo your simulation. Okay. The last thing is optimization. After you finish with, you test your all input parameters on all different scenarios, you come to the traditional optimization techniques that requires gradient estimation. Gradient may be difficult to you to understand. It means that nonlinear, or okay, if you studied a differential equation, the equations of if you have the first degree of differential equation of a system, it means that you had its gradient estimation. Okay, gradient means there's like the slope of the system. As with sensitivity analysis, the current approach for the optimization requires intensive simulation to construct an approximate surface response function. I mean by that that if you build your system and you draw your system behavior such that, like, say that your system variable is a curve just like this, then you have your gradient, you have your sensitivity. You will expect what's going on with your system. If your input is like this, your output should be around these numbers, for example. If you have the gradient of the system, you will anticipate, you will foresee your output if your input parameters have a specific set. The last thing is report generation. After you finish everything, you can report generate for a critical link. Report generation is very important in network simulation. In report generation, you can log all your input parameters and variables and the results in a diagram or in a list of numbers, so you will understand what is going on in your system. That's all for this lecture. It's too small but it's very important, because you have to understand these terms, and they are very, very important in simulation, not in network simulation only, but in any simulation you will encounter in the future. Thank you.